Have you ever wondered if something could be in two places at once? It sounds like science fiction, but it's the reality of the quantum world. At the quantum level, the rules of everyday experience break down. Particles, the building blocks of reality, can exist in multiple states at once. This is called superposition. Imagine an electron. Where is it? Classical intuition says it must be somewhere specific. But quantum mechanics tells us, before we measure, the electron isn't in one place. It exists in a haze of possibilities. It's not just that we don't know where it is, the electron genuinely occupies multiple potential states at the same time. Think of a spinning coin. Before it lands, it's both heads and tails. Superposition is the quantum version of that, but for properties like position or energy. This idea is jarring. It challenges our understanding of existence. How can something not be in one place until we look? This is the gateway to the quantum world. Superposition is the key to many of quantum physics' deepest mysteries. It's a journey into the weird, the wonderful, and the utterly fundamental. The universe at its core embraces ambiguity, and that's where our story begins. For centuries, classical physics described a predictable universe. Newton's laws let us calculate the future of planets and billiard balls alike. Everything had a definite state. The universe was a grand, knowable machine. But as scientists probed the atomic scale, classical rules failed. Light and matter behaved in ways that defied old physics. Enter quantum mechanics, a new framework built on probabilities, not certainties. In quantum mechanics, particles are described by a wave function, a mathematical map of all possible outcomes. The wave function doesn't say where a particle is, but the probability of finding it somewhere if we look. The Schrödinger equation governs how this wave function evolves, just as Newton's laws govern classical motion. So, we have two worlds: the predictable, definite world of classical physics, and the probabilistic, fuzzy world of quantum mechanics. At the fundamental level, the universe is not as clear-cut as we once thought. It embraces chance and uncertainty. The wave function is our tool for navigating this strange landscape. Quantum mechanics is a profound shift in how we see reality. Superposition means a particle exists in a combination of all its possible states until measured. It's not just uncertainty, it's genuine coexistence of possibilities. Each possible state contributes to the overall wave function. Imagine two quantum states, A and B. A particle can be in a mix, 30% A, 70% B, or any combination. Like mixing red and blue to get purple, a particle's state can be a blend of locations, energies, or spins. The most famous illustration is Schrödinger's cat, a cat in a box alive and dead at the same time until observed. The cat's fate is tied to a quantum event. If the atom decays, the cat dies; if not, it lives. Until we look, the system is a blend of all possibilities. We don't see cats in such states in real life because of decoherence, but the thought experiment shows the strangeness of superposition. Before observation, the system is a mix of outcomes. Measurement forces the system to choose a definite state. This is the essence of superposition, a state of coexisting possibilities. It's quantum reality at its weirdest. Is superposition just theory? The double-slit experiment proves it's real. Fire electrons one by one at a barrier with two slits. If they were classical particles, you'd see two bands on the screen. But you get an interference pattern, stripes, like waves passing through both slits at once. Each electron's wave function goes through both slits, interferes with itself, and creates the pattern. The electron is in a superposition of both paths. Try to detect which slit it goes through, and the pattern vanishes. Now you see two bands, as with classical particles. Observation destroys superposition, forcing the electron to choose a path. This is the observer effect. Measurement changes the outcome. The double-slit experiment is the clearest demonstration of superposition's reality, and its fragility. Its quantum strangeness, made visible. The double-slit experiment shows that measurement plays a crucial role in quantum mechanics. When we observe a quantum system, its superposition collapses into a single outcome. This is called wave function collapse. The maybe becomes anise. Why does measurement destroy superposition? The answer lies in decoherence. The environment, light, air, or measuring devices, constantly interacts with quantum systems, leaking information and forcing them into definite states. Decoherence happens almost instantly for large objects, which is why we don't see superposed cats. maintaining superposition is a huge challenge, especially for complex systems. The quantum maybe is fragile, requiring extreme isolation. Physicists use ultra-cold temperatures and vacuum chambers to protect quantum states. Understanding and controlling decoherence is vital for quantum technology. The observer effect and decoherence reveal the delicate dance between quantum systems and our attempts to measure them. Superposition's fragility is both a challenge and an opportunity. Superposition isn't just a curiosity, it's powering a technological revolution. Quantum computers use qubits, which can be 0, 1, or both at once thanks to superposition. This lets them process vast numbers of possibilities in parallel. With just a few hundred qubits, a quantum computer could outperform classical supercomputers on certain problems. Superposition also enables ultra-sensitive quantum sensors, detecting tiny changes in the environment. Quantum communication uses superposition to create secure channels. Any eavesdropping disturbs the system. Scientists are making progress in creating and maintaining superposition in larger systems. New materials, control techniques, and error correction are extending coherence times. The quantum dream, harnessing superposition for real-world technology, is becoming reality. The future is being built on quantum maybes. Despite quantum mechanics' success, deep mysteries remain. The measurement problem asks, what counts as a measurement and why does it collapse the wave function? Is it consciousness, complexity, or something else? No one knows for sure. The Copenhagen interpretation says collapse just happens when we measure. The many worlds interpretation claims all outcomes happen, each in a parallel universe. Bohmian mechanics and objective collapse theories offer other explanations. Each interpretation paints a different picture of reality. These questions aren't just philosophical, they could lead to new physics. Understanding wave function collapse might reveal links between quantum mechanics and gravity. The quantum frontier is still full of puzzles and possibilities. Superposition reshapes our perception of reality. The quantum world is a realm of potentialities, not certainties. Our classical intuition struggles to grasp this, but experiments confirm it's true. Embracing quantum strangeness means accepting the limits of everyday understanding. The rules of the quantum world demand a new kind of logic. Superposition is the foundation for future technologies, quantum computing, sensing, and communication. By learning to control superposition, we're harnessing the universe's most fundamental features. The journey from theory to technology is underway. Superposition challenges us to be curious and open to the unexpected. The quest to understand quantum reality continues. The quantum world invites us to marvel at the strangeness and wonder of the cosmos.